Okay, so we're going to take a look at example number 17 on your homework practice packet. And in this particular example, there are applied forces that are moving at an angle. So, as I mentioned before, kind of the dreaded wonkavator, elevators that move up and down and a little left to right as well. So, it says an applied force of 50 newtons. So we have an applied, or the force of our pull, is equal to 50 newtons. At 25 degrees up of east, is applied to a 7 kilogram crate, so the mass is 7 kilograms. To slide it across the floor, determine the coefficient of friction. So our coefficient of friction is x, and we know that if we want to calculate the coefficient of friction, we have to know the force of friction, and we also have to know the normal force. And then it says if it accelerates, so our net acceleration is equal to 3.0 meters per second squared. So let's include some other pieces of information that are hidden. We have the force of gravity, which is negative 9.8 meters per second squared. Or excuse me, the acceleration due to gravity, not force of gravity. And we also know that typically when we solve these problems, getting the weight is going to be helpful for us too if we are given the mass. And if you notice, we're given the mass, so we're going to want to calculate weight. So what do we do first? Well, we listed everything that we needed. So the next thing that we're going to do is draw a free body diagram. So we're going to draw a free body diagram. So the box now becomes a dot. And we have the force of friction that's going to pull back on this dot. We have the force of gravity that's going to pull down on this dot. We have the normal force that is going to pull up. And we have the applied force, which is going off at an angle. So the force of the pull here is 50 newtons. So in this case, we see an angle here. It's going to be very helpful for us to give ourselves a nice little handy-dandy triangle because we need to know that this is 25 degrees as well. So we listed all our variables, we drew our free body diagram. The next step that we're going to do, of course, because it's going to be helpful for us no matter what, is we're going to calculate the weight. So we're going to take a look at this. We've got W is equal to mg. Our weight, we don't know what it is. Our mass is 7 kilograms, and gravity is negative 9.8 meters per second squared. So in this case, our weight, using our calculator, is 68.6. So our weight here is negative 68.6 newtons. So we're going to fill that bad boy in for the force of gravity. Negative 68.6 newtons. So now, the next step, what we would normally do if we had these not at an angle is we would calculate the normal force, and the normal force is just the reverse of this, if you remember, because the net force in this direction is 0. But in this case, we're getting a little bit of help because part of this force is helped here. Remember, the normal force only applies exactly what it needs to keep things all nice and balanced. So we're going to have to figure out what this little length is here and how much help the normal force is actually getting. So I like to call this the little y, because we have to calculate, we're going to eventually calculate this little y, and I like to call this the little x because it's just one little piece of the puzzle. So the next step that we're going to do is we're going to calculate the little y. So if we look here, we've got the y, which is opposite, ding, 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 opposite, and we have a hypotenuse. So opposite and hypotenuse means that we have to use sine. So the sine of 25 is equal to our opposite, which is y, over 50. So we have sine 25 times 50, and our little y value is sine 25 times 50. We get 21.13. So our little y value is 21.13. Okay, so in this case, typically the normal force would be a positive 68.6, but we're getting help with this 21.13. So our normal force in this case is going to be what the normal force should be, which is 68.6. minus the help that it gets, 21.13. So the normal force 68.6 minus 21.13. We get 47.47. So our normal force in this case is 47.47 newtons. So let's go fill that in up here. And let's also include it on our free body diagram, just so that we have it. Okay, so we got our y direction taken care of. Now we got to take care of our x direction. So in this case, our box is getting pulled upward or at an angle, so not everything is getting pulled directly this way. So we've got a little bit of extra help in this y direction, so this x is not as big as 50 because together it makes up the 50. So what we're going to have to do here is figure out what our little x value is to figure out what the applied force is in the x direction. So after calculating little y, we calculated the normal force by subtracting the little y value from the positive expression of the force of gravity. So we got our normal force. Now we're going to calculate our little x. Okay, so our little x in this case, if we go back to our little picture here, we have x here is an adjacent and we have a hypotenuse. So we're going to use cosine of 25 is equal to x over 50, or we get cosine of 25 times 50, which gives us 45.31. So our cosine is 45.31. So we're going to go fill that in right up here so we know what that value is. So we get 45.31 for our little x. So now what we're going to have to do is calculate the force of friction. So in this case, we have to take a look at the net force. So remember, we use W equals mg in the up and down direction, which we did over here. Now going this way, we have to use F equals ma. So we're going to use our net acceleration, or we have to calculate our net force. In the x direction. So in this case, we have F net is equal to mass times acceleration. And in this case, our F net is going to be equal to the mass, which is 7, times the acceleration, which is 3. So our F net is going to be equal to 21 newtons. And our net force equation in this case is F net is equal to the force of friction plus the force of that little x. So now we have 21 is equal to the force of friction plus 45.31. So we're going to subtract 45.31 from both sides. So now we get 21 minus 45.31. And we get negative 24.31 for the force of friction. So let's go fill that in up on our diagram. And up over here. Okay, so we have our force of friction and we have our normal force, so guess what we can calculate? Ta-da! We're going to calculate mu. So we calculated the F net in the x direction. Then we calculated the force of friction. Last step, solve for mu. So we have force of friction. Mu is equal to the force of friction, which is negative 24.31, but remember we don't deal with signs, divided by the normal force, which is 47.47. And we get 0.51. So mu is equal to 0.51. And wouldn't you know it, 0.51 for number 17 is letter choice A. And we got it right because we're very smart. Now go forth and be excellent.